is Omrit Filzer, and I will tell you about Condorcet relaxation in spatial voting, and this is a joint work with Arnold Filzer. So this figure is taken from a website called thepoliticalcompass.org, and what you see here is a simplified representation of the economic and political views of some well-known people and also some countries. And this is represented simply as a set of points in two-dimensional Euclidean space. So naturally, if 2 points here are close to each other, it means that they are representing similar political views. More formally, we define our voting system as follows. We are given a multiset of voters, which are points in some metric space XD, and their goal is to reach a joint decision, or in other words, decide on some policy, which is also a point in the metric space. The voting rule would be that a voter V prefers a policy P over another policy Q if its distance to P is smaller or equal to its distance to Q. Now, which policy would win the vote? So one way to decide the winner is using the well-known Condorcet criterion. A Condorcet winner is a point who would win a two-candidate election against any other point in a plurality vote. And this means that it would win at least half of the votes against any other candidate. In spatial voting, we focus on the case where the metric space is Euclidean, in some dimension D. This looks just like the figure that I showed you on the first slide, and this special case was indeed studied by various researchers in the political economy context. Now let's look at an example for D equals 1. So the voters are just points on the line, and the question is it or exist a Condorcet winner? In other words, we are looking for a choice point on the line who would win at least half of the votes against any other candidate. And again, remember that a voter will prefer the point which is closer to it. So it turns out that this one-dimensional case is very simple, and actually the median point always wins. Let's see why. So in a match against any point to the right of it, it will win all the voters to its left. So it's at least half of the vote. And similarly, in a match against any point to the left of it, it will win all the voters to its right. So again, at least half of the vote. Now, an unfortunate fact is that for dimensions larger than 1, a Condorcet winner does not exist for most sets of voters. Let's consider a simple example with 7 voters. And notice that they are arranged on this almost equilateral triangle. The first guess about the location of a Condorcet winner would be just take the middle point. But you can see that this red candidate wins strictly more than half of the vote. Okay, let's try something else. Maybe a Condorcet winner is somewhere on the middle of one of the edges of the triangle. Well, it loses again to a red point, which is on another edge, but a little bit closer to one of the vertices of the triangle. And it's not hard to show that for this example, there is no Condorcet winner. So what can we do if we still want to reach a joint decision? One way is to define some relaxation on the Condorcet criterion. Beta would be the relaxation parameter. And again, we have a set of voters V in a metric space XD, but now the voting rule changes. We say that a voter V beta prefer a choice P over another choice Q if beta times its distance to P is not larger than its distance to Q. Now, instead of Condorcet winner, we define a beta plurality point for the set V to be a point P in the metric space, such that for any other point Q, at least half of the voters beta prefer P over Q. This notion of beta plurality was originally defined by Aronov, de Berg, Goodmanson, and Horton in a paper published in the last Sausage Conference. Now notice that when beta equals 1, A beta plurality point is a Condorcet winner. This means that we are getting closer to having a Condorcet winner as beta is getting larger. Let's look at the example that we had earlier that had no Condorcet winner and now set beta to equal half. You can check and see that the middle point is now a plurality point for this parameter. Because if we take any other point, for example, this red point, it will never win more than half of the votes with this new voting rule, which gives some advantage to the blue point. So in this case, the red point will not get any votes because for each voter, its distance to the red point is larger than half its distance to the blue point. And here the red point do win this 3 votes at the bottom right corner, but this is not enough because the blue has 4 votes. This leads to the algorithmic question, which is, given a set of voters V, what is the largest beta for which V admits a beta plurality point? More formally, we define beta xt of V to be the supremum over all values beta such that V admits a beta plurality point. So Aronov et al. In their paper showed that there exists an efficient polynomial time approximation algorithm for computing this beta of V for the spatial case, when the metric space is a d-dimensional Euclidean space. So we know that if the algorithm gives us relatively large beta, it means in some sense that for this specific set of voters, we are close to having a Condorcet winner. But this raises the following question. Given a metric space XD, what beta should we expect to get? In other words, how good is the metric space for this voting system? Or what is the amount of relaxation that we need in order to reach a stable decision for any set of voters in the metric? Now consider the following existential question. Given a metric space XD, what is the largest beta such that every multiset V in X admits a beta plurality point? And more formally, we define beta star of a metric space XD to be the supremum over all values beta such that every finite multiset V in X admits a beta plurality point. Aronov et al. Consider this question as well. And for the case of the 2-dimensional Euclidean space, they show that beta star is at most square root 3 over 2. And this means that there exists a set of voters in the plane for which there is no beta plurality point for any beta larger than square root 3 over 2. The set of voters in the proof is simply 3 points on the vertices of an equilateral triangle, and they have a very nice proof showing that the parameter beta of this set of voters is at most square root 3 over 2. On the other hand, they also showed that for any set of voters in the Euclidean plane, there exists a square root 3 over 2 plurality point, which means that this is also the lower bound, and we get that beta star of the Euclidean plane is exactly square root 3 over 2. For the case of higher dimension Euclidean space, they showed a lower bound of 1 over square root d. So for every set of voters V in RD, there exists a 1 over square root d plurality point. So parallel to our paper, the case of the Euclidean plane was closed. It is exactly square root 3 over 2. But for higher dimensions, there was a pretty large gap with unbounded ratio depending on the dimension d. In our paper, we managed to get a constant lower bound for any dimension d. We show that beta star of the d-dimensional Euclidean space is larger than 0.557, which means that for d larger or equal to 4, the gap shrinks and the ratio is now constant. Now, more than that, we actually give a constant lower bound for any metric space. So take any metric space XD and any set of voters in X, there always exists a plurality point with parameter square root 2 minus 1. In addition, we show that there exists a metric space with beta star smaller than half. In this talk, I will focus on showing you these last two results for a general metric space, and our technique for showing the lower bound for the Euclidean space is an extension of this. Okay, so for general metric spaces, we ask ourselves how small can the parameter beta star be? Or more formally, we define beta star without a subscript to be the infimum of beta star of XD over all possible metric spaces. First, we give a lower bound on beta star and show that it is at least square root 2 minus 1. Then we show that it is at most half. So this is an upper bound. And finally, we get that beta star is in the range between square root 2 minus 1 and 1/2. Let's start with the first theorem. To show that beta star is at least square root 2 minus 1, we need to show that for any metric space and every set of voters, there exists a square root 2 minus 1 plurality point. So first, for any point P, we let Rp be the minimum radius such that the ball with radius Rp around P contains at least half of the voters. And now let P star be a point with the smallest radius Rp star. So in this figure, we have the point P star, and this ball with radius Rp star contains at least half of the voter set, and Rp star is minimal. So for any other point, we will need a larger ball. Now we claim that Rp star is a square root 2 minus 1 plurality point. And let's set beta to be square root 2 minus 1. Now let's look at another point Q in the metric space and consider the ball around Q that contains at least half of the voters. So it has radius RQ, which is larger or equal to Rp star. And we are considering the open ball without the boundary. So this ball cannot contain half of the voters. The number of voters in the open ball is strictly smaller than V over 2. Now notice that if these two balls do not intersect, then P definitely wins all the voters inside its ball, and we are done. Otherwise, we have two cases. First, assume that the distance between P star and Q is at least square root 2 times Rp star. So this is the case where Q is far enough from P star. In this case, we can show, using triangle inequality arguments, that every voter from the ball around P star is close enough to P and far enough from Q. So it will better prefer P star over Q. The second case is that Q is close to P, when the distance between P star and Q is at most square root 2 times Rp star. In this case, we can show that every voter that is located outside the open ball around Q will better prefer P star over Q. And this is because the distance between P star and Q is small enough comparing to beta. Now, since there are at least half of the voters outside this ball, we get that P star wins again. And this concludes the proof. Our second theorem shows that beta star is at most half. And for this, we need to show an example of a metric space and a set of voters such that there is no beta plurality point for any beta strictly larger than half. So the metric space that we choose is a continuous cycle of length 1. And the distance between 2 points is the shortest path on the cycle. Assume that beta is strictly larger than half. we choose our voter set to be these 3 points equally spaced on the cycle. So V1 is at 0, V2 is at 1/3, and V3 is at 2/3. Consider a point P a distance alpha from V1, and we can assume that alpha is between 0 and 1/6 because all the other cases are symmetric. We will now show that P cannot be a beta plurality point. Consider another point Q located at half minus alpha over 2. Now, if we compute the distances between Q and V2 and P and V2 in terms of alpha, we get that the distance between Q and V2 is smaller than beta times the distance between P and V2 for any beta larger than half. This means that V2 would not beta prefer P over Q. And the same is true for V3. So both V2 and V3 would vote for Q, and P will lose the elections. This shows that for this specific set of voters, we need beta to be smaller or equal to half. And in the paper, we actually also show that for this metric space, beta star equals to half. So this is a worst case example. To conclude the talk, we show constant upper and lower bounds for general metric spaces, and also give constant lower bound on beta for the case of spatial voting. However, we only have a tight bound for the two-dimensional case, and even though we managed to prove a much smaller gap with bound and ratio, closing it is still a very interesting open question. Our conjecture is that beta star equals half, and for the Euclidean case, beta star is square root 3 over 2 for any dimension d larger than 2. And the reason is that the equilateral triangle is probably the worst case example, because having only 3 voters means that a plurality point must win a fraction of 2/3 of the overall vote. And if we add more points, this fraction only decreases. And finally, if indeed the beta that we need in spatial voting is square root 3 over 2, which is approximately 0.866, then it means that the amount of compromise or relaxation needed in order to find a winner in such a voting system is relatively small, which is a desired property of a metric space. Thank you very much. Hope you enjoyed this talk. Bye-bye.